And now let's look at infinite limits of sequences at infinity. So if an becomes large as n becomes large, we use the notation, and we use this one, limit as n approaches infinity of an, this equals to infinity. And yeah, this just means that the limit is going to infinity. This is diverging to infinity, as I'll explain, as n goes infinity. So the following precise definition is similar, put a space here, similar to my earlier video's definition. A definition for infinite limits at infinity, and let's go over that. This is going to be definition 3. So definition 3 states the limit n approaches infinity of an is equal to infinity. Yeah, this means that for every positive number m, there is an integer n such that an is going to be greater than this positive number m whenever n is greater than n. So very similar, but instead of an interval, now we just have a greater than a number because it's going to infinity. Yeah, so thus for any number m, regardless of how large it is, the sequence has a point that is larger, i.e. always increasing. And you can always determine that where n is greater than this specific number n. And compare with my earlier video's definition for infinite limits at infinity. This one say let f be a function defined on some interval a at infinity, then the limit as x approaches infinity of f of x equals to infinity. Means that for every positive number m, there is a corresponding positive number n such that if x is greater than n, then f of x is greater than m. It's the same thing as whenever you could use if then. It's exactly the same thing. So graphically, both these definitions are illustrated below, and I've just made it for f of n equals to an, where yeah, again it's integer, where n equals to integer greater than 0, positive integer. So just to illustrate both at the exact same time, just write it that way. So we have, let's say we have x and we have n, we have y and we have a n like this, and let's say we have a graph that goes like this. This is 0, it goes up like that. So we have y equals to f of x like that, and it's going to infinity. And let's say, so then if it's going to infinity, then there's always a number m over here such that this number m corresponds to a number n, in this case an integer for our other case. So, but right now it's going to be a number n, so that's all we do is replace a positive number with positive integer. So there, integer n, like that, such that we have f of x is greater than m. So we could, for n is greater than, if x is greater than n. So for example, to the right here, we have x is greater than n. Or, yeah, I'll do the integer ones after. So if x is greater than n, for example, we'll always get a point like this right here, where this is x is greater than n, and this is right here, and it corresponds to a number all the way across here, where f of x now is greater than m. So this height is greater than this one, and this one is to the right, when x is greater to the right of n. And likewise for sequence, let's say 1, 2, 3, 4, that corresponds to the function. So we have this, and it's the exact same thing but in sequence form. So say it keeps going up, and then we have, so we have this corresponding stuff like that. So if there is a number m corresponding to n like this, or integer like that, doesn't need to be, actually yeah, it should be on it actually. It says it's corresponding to an integer that, say it's connected right on it, then it goes over here. Yeah, actually to illustrate this a bit better, this needs to be on the integer because that's integer n, but this doesn't need to be on it. It could be somewhere across here. It could be somewhere across there, for example. Yeah, it could be there or below, or it doesn't matter. Any number you pick, you're always going to have an integer where when you get bigger than it, for example, this one there is going to be bigger. So for example, so that's integer, this one right here is, well, that's an n that's bigger than this one, n is bigger than capital N. So to the right we have x is greater than n and n is greater than n. And then this point right here, this one here is, well, all the way across, this is just n is greater than n, and this one here is an is greater than n, where again these points are just an, and in our case equals to fn. For this illustration, just leave it like that. So yes, very, very interesting stuff. So that's all it means. So at any point, if it's actually increasing, you could always find any number, however large it is, you'll find a corresponding a number or integer n such that the function will be bigger than it when x or n is bigger than capital N. Yeah, so thus again, this graph needs to be valid no matter how large n is chosen. And now is when make another note. Note if we have the limit, so if the limit is going to infinity, so if, just for notation, if limit as n approaches infinity of an is equal to infinity, yeah, then an, the sequence is divergent, but in a special way, when we say that n diverges to infinity, or using that symbol like that, infinite 8 symbol, horizontal 8. So, yeah, that's just terminology.